Okay, so in this video lecture I'm very quickly going to review the operation of the circuit that you can see in front of us just now, which is the one-bit arithmetic logic unit. So as you'll probably know from the lecture note, the example that we'll be considering is really a toy example. It's so simplified that it wouldn't really be much use inside a proper computer, but it illustrates the principle by which ALUs work. And then, as we'll see at the end of this video lecture, you'll see that it can be aggregated to make a much more powerful arithmetic logic unit, which is what we did with the adder and the adder subtractor circuits. Before we move on to look at the ALU, it's worth just reminding ourselves of where the ALU actually exists. So the ALU is a part of the CPU, and this diagram, which is the diagram that we'll spend a fair amount of time looking at in terms of the work of the CPU, shows us the position of the ALU in regard of the other internal components of the CPU. So I suppose a couple of observations are worth making. ALU takes inputs from the scratchpad registers and also this MBR register over here. So you can see that at the top of the ALU in this diagram there is an input from the A bus, A input, and then from the B bus there is a second input which is known as the B input. At the bottom of the ALU you can see that there's an output onto the C bus, and that C bus connects to other components inside the CPU. So we don't need to worry about that in too much detail at the moment, but we'll just note that the ALU takes two inputs and has a single output. And then I suppose the other observation to make is that the ALU is under the direct control of the control unit. So again, we'll find out in more detail later on in the lecture sequence what the purpose of the control unit is, but at the moment all we'll say is that it's in charge of the operation of the ALU as well as the other components inside the CPU and also the primary memory. So this is the circuit that we'll be looking at in a fair amount of detail. It's the one-bit ALU, and I suppose that if we were to decompose it into its various components, the most notable feature will be the three sub-circuits that are contained within the ALU circuit. So you can see that the most recognisable part of the circuit is of course the full adder sub-circuit, and you can see that the inputs to the full adder circuit can be traced back through the circuit design to the inputs A and B to the circuit, and also the carry in to the circuit. The other notable component is the logical unit, which consists of three gates which are responsible for computing the functions of the ALU, the three Boolean functions of the ALU. So you have an AND gate which is used to compute the Boolean AND of A and B. You have an OR gate which is used to compute the Boolean OR of A and B, and then you have a NOT gate which is used to compute the negation of whatever value is input to B. And then the third notable component, the final component that we'll discuss, is the decoder. So the function of the decoder is basically to select which of the four available computational functions will actually be output out of the ALU. So when we simulate this circuit in Logisim, what we'll observe is that the ALU takes inputs from A and B and the carry in, and it computes all four functions simultaneously. So it does the addition of A and B and the carry in, it does the AND of the A and B, the OR of the A and B, and the negation of B, and it does those four functions simultaneously. Now obviously you can't have the outputs of all four functions simultaneously outputting from the circuit, so it's the role of the decoder to actually select one of those outputs. So the decoder takes inputs from F0 and F1, and basically on the basis of those inputs will cause one of the outputs of the four computational functions to be routed out of the circuit. So what we'll do next is we'll put this circuit into Logisim, and I'll work my way through the different four functions and we'll make a few more detailed observations consistent with what we've just discussed at this point. Okay, so now we're looking at the ALU circuit simulated in Logisim, and you can see that we have really what is an identical copy of the circuit that was presented to you in the lecture note. So what I'm going to do, first of all, just to demonstrate that the circuit does behave in the way that it's supposed to do, is I'm going to do a basic addition. Okay, so the process of activating the circuit I'll always do as a three-step process. So I'll assert a step 1 values to A and B. I'll then go down to the function pins and I'll select the function that I want the circuit to compute, and then for the third step I'll enable A and I'll enable B in order to activate the circuit and to observe then the output. So the first thing that we'll do is we'll add 1 and 1 together. We'll add A equals to 1, we'll add B equal to 1, and we'll add the carry in equal to 1. So I switch the mode of Logisim to simulation, and when I do that I can then activate the 3 data pins, A, B and the carry in. They're now all set to 1 and 1. So that's step 1, and then I go to function 0 and I set that to 1, and I set function 1 to 1. Now you can see that I've labelled the function pins with a text label which basically lays out what each combination of binary inputs to the function pins actually does in terms of activating the circuit. So if I select 1 and 1 for both F0 and F1, then the circuit will perform an addition. So that's step 2 carried out, and then finally I enable the inputs A and B by activating the enable pins, enable A and enable B. Now the inputs were A and B and the carry in equal to 1, so that's the same thing as adding 1 plus 1 plus 1, which, as you'll recall from your binary addition facts, is equal to a sum output of 1 and a carry out of 1. So that seems to be entirely in order, and we can, while the circuit is active, look at the individual components and just make a little bit of an observation. So the first thing I'm going to observe is that if we trace A and B, we can see that the first thing that they pass through is these 2 AND gates. So these gates, the AND gates that we see here, these 2 here, they're what I would call, if you like, enable gates that can control whether a circuit, an input to a circuit propagates into the circuit or whether it does not propagate into the circuit. So basically if we look at A there, you can see that A as its input to the AND gate is a 1 and the output of the AND gate is also a 1, and yet if I go and switch off enable A, you can see that the output of the AND gate is also switched off. So enable A basically allows us to control whether the input signal at A actually gets into the circuit and then propagates through the circuit. So that's the first observation that I want to make. The other thing as well is that if we look at the AND gate, the OR gate and the NOT gate, we can see that they are active in terms of the inputs that they receive from A and B. So we can observe that the AND gate is computing the AND of A and B when the circuit's enabled. The OR gate is computing the OR of A and B when the circuit's enabled, and the NOT gate is taking the input from the B input and it is negating it. You can also see the A and B, if you trace through the wires that exist inside the ALU, that they are also being propagated into the full adder, and you'll see also that the full adder is active and carrying out its computation. So then the question is, how does the circuit select from these 4 simultaneously computed functions? And the answer of course resides down here with the decoder part of the circuit. And if you look at the decoder part of the circuit, you can see that there are 4 AND gates. Now each of these AND gates is connected to a special line which is known as an enable line. So the idea with the decoder is that only one of these AND gates can be switched on at a time. Only one of the emerging enable lines is active at a particular time, and depending on where the enable line is routed to which circuit is connected, it will either switch on the outputs of the full adder, or it will switch on the outputs of these three Boolean logic circuits up here. Now if we look at the AND gate, which is active at the moment inside the decoder, and follow the line, we can see that it connects to the AND gates, which are internal to the full adder, and which, when they are activated, allows signals to propagate out of the AND gate. This is also true up here as well, of this AND gate here. So let's undo our step-by-step process. So we'll switch off A, and then we'll switch off B. So now the circuit is disabled, and we can go back to the beginning of the process and assert new values for A and new values for B, and also select a new operation. So let's do that. Let's do A and B equal to 1 and 1, so they're already set. And instead of doing an addition operation in step 2, what we'll do is we'll do a Boolean AND operation. So to do that, you have to set function 0 and function 1 equal to 0 and 0. That's now done. And then what we do is we complete step number 3. We enable A, we enable B, and we can see that the output of the sum, or the output is A1. So you have to keep in mind what the AND function does. The AND function is known as the all or nothing gate, and basically if all of its inputs are 1, then the output of an AND function will be 1, and in case of any other combination, the output will be 0. So remember that it's this AND gate here that does the ANDing computational function of A and B. And again, if we look at the decoder, you can see that the line which is enabled at this point is the line that's connected to the first AND gate inside the decoder, and if you follow that line up, you'll see that it connects to another AND gate which is also connected to the output of the AND gate, which is doing the actual computation of AND A and B. So you can then see that that is the function which is going to be routed out of the circuit by the decoder. So that's grand. We'll switch off enable A and enable B, and then what we'll do is we'll do 1 0, which will activate the negation of B. So we can just set A to 0, we won't be needing it for this example, and then what we do is we switch on B, we set B to 1, and we'll switch on the negation function. You can see that when I do that, a different enable line is activated, and if we follow the single active enable line, we'll see that it goes to an AND gate up here, which is in turn connected to the NOT gate over here. So we'll enable B, and you can see that the input of B, which is 1, propagates into the circuit, becomes an input to the NOT gate and the OR gate and the AND gate, and also the full adder, and then the negation of B emerges from the NOT gate and makes its way to the AND gate, which has been enabled. Now, of course, if one of the inputs are 0, then the output will be 0. So we don't talk about the AND gate being switched on, but what we do note is that the effect, the overall effect of it being disabled, is for it still to emit the correct value. So the negation of B is, of course, 0, and that's the output that propagates to the output pin of the circuit. So for the sake of completeness, if I just dot over here and switch B from 1 to 0, you can see that the AND gate, the NOT gate produces the negation of B, which is now 1, and the AND gate is fully enabled, and you can see that it propagates out of the circuit like so. Okay, so we'll switch off enable B, and then we'll do our final function, which is the OR function, which is 0 or 1. And remember that if any of the inputs to an OR gate are high, then the OR gate will go high. So what we'll do is we'll set B equal to 1 and A is equal to 0, and then we'll enable B and we'll enable A, and we can see that the OR gate is taking a 0 from the A gate, the A input, and a 1 from the B input, and we can also observe that the enable gate for the OR function is switched on by the decoder, and we can observe the value making its way to the output of the circuit. Okay, so I'll switch that off. What we'll do next is the same thing that we did with the adder subtractor circuit. We'll look at this circuit in its packaged form, and we'll observe that by aggregating 1-bit ALUs together, we can actually create a fairly powerful aggregated circuit. Okay, so I'm now looking again at the ALU circuit, and what you can see is if you look at the tool pane to the left hand side of the screen, I'm going to switch to a circuit that I've already prepared. You can download this from Blackboard, which is called the ALU 4-bit, and basically you can see that I've taken a bunch of 1-bit ALUs like so, and I've packaged them, and then I've wired them up so that they are connected to function pins F0 and 1, enable A and enable B, and then the input pins for the A word, the B word, and then the output pins for the actual circuit itself. So this is a 4-bit ALU, and we can use it to perform addition, Boolean AND, Boolean negation, and OR. So I'll just follow the same process that we did previously. What I'm going to do is switch the circuit to simulation mode, and I'm going to assert that the 4 inputs to A will be 0, 1, 1, 1, which is decimal 7, and then I'm going to assert that B will be 0, 1, 0, 0, which is 4. So I'm going to set the circuit in the second step to do an addition by asserting that F0 and F1 are 1 and 1, and I don't need to set the carry into any value, but I'm going to then proceed to the third step, which is enable A and enable B. And if we look at the outputs over here in the top right hand corner of the circuit, we can see that we've got 1, 0, 1, 1. So 4 plus 7 would be 11. So that's 8 plus 2 is 10 plus the 1, that gives us our 11. So we can see that the circuit will do addition, and I guess like every time we've aggregated circuits in the past, what we can see immediately is that we get much more power from doing that aggregation. So obviously I could have carried on and I could have added more ALUs, but of course that would have been more complex for me to wire together, and I think that in principle you would accept that I could have done an 8-bit ALU or a 32-bit ALU, and it would just as obviously have behaved in the way that we can see here with the 4-bit ALU. So I'm not going to do all of these just now. I'm going to switch off A and B, and I think what I'll do is I'll select negation. We'll do the negation of B. So if you observe the circuit, you can see that it is 0, 1, 0, 0, and if I enable B, you can see that the output, okay, sorry, what have we done there? What have we forgot to do? It must be OR, so we'll try it like that. Enable B, no, that's not right. 1, 0, enable B, yeah, there we have it now. So yes, B is 0, 1, 0, 0, and you can see that the output is 1, 0, 1, 1, which is the negation of the B word. Each of the bits of B has been flipped. 1s become 0s, 0s become 1s, and again that's how the circuit should behave. So I'll do, just for the sake of finishing off, AND. So AND is function lines being set to 0 and 0, and what we'll do is we'll AND together 1, 1, 1, 1, that's the A input, with 0, 0, 1, 1. Now the type of operation that's done here is known as a bitwise operation. So all we're doing is looking at the first digit of A and the first digit of B and ANDing them together. So if you have forgotten what that means, you should go back to, I think, lecture number 3 and just very quickly review the AND function and look at the truth tables for a 2-input truth table. But basically A0 is ANDed with B0. A 1 and 1 will give you an output for the AND function of 1. A1 is ANDed with B1, that's 1 and 1, so that will also give you an output of 1. And then A2 is ANDed with B2, which is 0, so we'll expect to see an output of 0. And then A3 is ANDed with B3, and we'd expect to see an output there also of 0. So the AND function is got by selecting F0, 0 and F1, 0, and then enabling A and enabling B, and right enough we can observe the output there, which is 0, 0, 1, 1, and that's the bitwise AND function of the ALU, of the inputs A and B. And then finally, the last circuit that you can see is the packaging up of that into a circuit in its own right, and you can experiment with that. You'll see that that has the similar functionality, and I guess if we wanted to, we could carry on onto another circuit like so, and we could take our 4-bit ALUs and wire them up like so. So I'll let you do that yourself, and good luck with it. There's a lot of wiring once you get into these more complex circuits. The problem is not so much specifying the circuits, but finding the room to actually put the wires in without causing yourself problems. Okay, so anyway, that's the ALU. You're strongly urged, as ever, to download the zip file from Blackboard that contains this circuit and to experiment with it, review the lecture notes as well, and good luck with that. Thank you very much. Bye-bye.